Hello students. Today we will be learning about sequences and series. The introduction part, how we define sequences and series. We are going to see some examples also. Mainly we are going to cover section from 8.1 to 8.3 of NCERT. A small disclaimer. The images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. Thank you. Now, as I have told earlier, that we are going to discuss introduction, how these sequences and series are relevant in mathematics branch, and how we define our sequences. We are going to see some examples, and then series. What do we mean by series in mathematical terms? We are going to see some examples related to both sequences and series. So, when we say that a collection of objects is listed in a sequence, we usually mean that the collection is ordered in such a way that it has an identified first member, second member, third member, and so on. Basically, what is happening? So simply, you are having some kind of list, and that list in a sequence, meaning that we are having some identified first member of the list, then second, then third member, then fourth and fifth. You can easily identify that if someone says that what number, what position of this member, so you can easily answer that question. You can easily identify the position of any member in that list. Simple. So sequences following specific pattern are called progression. Clear? I hope that now you have somewhat vague idea about sequences. So sequences are nothing but simply a list in which you have identified members. You can easily identify the position of your members. Now, assume that there is a generation gap. So let's have an example. Using this example, you will have some sort of idea about sequence. Okay. So a generation gap of 30 years. We are asked to find the number of ancestors, meaning parents, grandparents, great grandparents, etc. that a person might have over 300 years. Simple question, simple understanding. We are having 30 years of generation gap. Yes, and we have to find out the number of ancestors over the span of 300 years. So the total number of generation is simply 10. How? Why? We are having the total span of 300 years, and every 30 years, in every 30 years, there's a jump. Simple. So we are having total generations, 10 generations. The number of persons, ancestors for the first, second and third till 10th generations are simply, so for first 2, 4, 8, 16, 32 till 1024 for 10th generation. Simple. Here we are having two parents, then parents, great grandparents, grandparents, then great grandparents, etc. These numbers form what we call a sequence, because you can easily say that what member of this list is at what position. So 8th is at simply 3rd position, 4 at 2nd position, and 1224 at 10th position. Simple. And you can easily extract the information you want to know. Now, we are going to see types of sequences. So first is finite sequence, meaning as the name suggests itself, finite. When do we say something is finite? When we have a real finite number to express the thing, the quantity. Simple. So a sequence containing finite number of terms. Terms meaning the members, the elements. So if you are having finite number of terms, then your sequence is going to be a finite one, finite sequence. For example, we have seen in previous example the sequence of ancestors, which is a finite sequence since it contains 10 terms. How many? 10 terms. Yes, a fixed number. So a definite number, a finite sequence. Now, infinite sequence, as the name suggests, infinite, in which you are not having a finite number to express, or not a finite sequence will be your infinite sequence. Simple. Example. So suppose you are dividing 10 by 3. Now, using long division method, the steps of division will be what? First you will get 3, and then 3.3, then 3.33, then 3.333, and so on. The steps never going to be end. Yes. So in this, what we are having? A infinite sequence in which the number of terms are going on. Simple. The various numbers occurring in a sequence, so these numbers A, 3, 3.3, 3.33, and so on, we are going to call these numbers as terms. Clear? Simple. What is terms? The members of your sequence. Now, terms of a sequence, meaning, so in general, your sequence will be denoted by A1, meaning first position member, A2, meaning second position member, A3, meaning third position member, AN, meaning nth position member, and so on. If you are having your infinite, then you will use 3 dots. If you are having some finite, then you will stop here, AN. Now, the subscripts denote the position of the term. So each term having this subscript 1, 2, 3 denotes what position of your term. A1 denotes the first position, A2 denotes the second, A3 denotes the third, AN denotes the nth position. Simple. Now, the nth term is the number at the nth position of your given sequence, which is denoted by a. Clear? The nth term is also called the general term of your given sequence. Simple. Of your given sequence. Thus, the terms of the sequence of successive quotients are, so by recalling the previous example, simply the first position term is 3, the second term is 3.3 denoted by A2, third term is 3.33 denoted by A3, and so on. Can you form a nth position term? Yes, an is simply denoted by what? In that you are going to have 3.333 till n minus 1 times 3. Yes, if you observe here, after decimal, how many 3 you are having? In this case, 1. So 2 minus 1. So 2 minus 1, yes. In this, after decimal, how many 3s you are having? 2, meaning 3 minus 1. And for nth position, you will have after decimal, how many 3s? N minus 1. Clear? I hope that you can represent your nth position term by an. Simple. Moving to next. Now, recurrence sequences. What do we mean by recurrence sequences? In some cases, an arrangement of numbers, such as, for example, 1, again 1, then 2, then 3, then 5, then 8, has no visible pattern. But the sequence is generated by the recurrence relation, meaning that the upcoming term is somehow related to the previous term or terms. In this case, we are observing that the first position term and the second position term both same 1. The third position term is nothing but the sum of the two previous terms, A1 and A2. So this is your recurrence relation, meaning your upcoming term is depending on the previous terms. Now, in general, a nth term is simply what? The previous two terms sum. So if a nth, this represents your nth position term. Now, I want the sum. This must be this equals to the sum of the two previous terms, just two previous. So the two previous terms is simply denoted by a n minus 1 term and a n minus 2 term, meaning n minus 1th position and n minus 2th position. Simple. So, and this particular example is a example of sequence which is Fibonacci sequence. Yes, what? Fibonacci sequence. So please do memorize this. This sequence is quite important. How we define it? What is its natural, not a natural? What is its nth form? Clear? So Fibonacci is your recurrence sequence depending on the previous terms. Now, recurrence sequences. So often it is possible to express the rule which yields the various terms of a sequence in terms of algebraic formula. Simple. Consider, for instance, the sequence of even natural number. meaning 2. The first position number is 2. Second, 4. Third term, 6, and so on. Now, how we are going to use in A1, A2, A3 form? Simple. A1 is nothing but 2, already given to us. We can rewrite this 2 as 2 times 1. A2 is 4. We can rewrite this as 2 times 2. A3 is 6. We can rewrite it as 2 times 3. A4 is 8. We can rewrite this 8 as 2 times 4. And so on. A23, quite simple. Without any difficulty, you can write your A23 is going to be 46, which is twice of 23. A24, without any difficulty, 48, which is twice of 24, and so on. So what we have observed from the first 4 terms, that the nth position is nothing but the nth term is twice of the nth. Simple. So second term is simply twice of the second, 2. Third term, twice of 3. Fourth term, twice of 4. And using this information, we can easily conclude that A23 is simply your twice of 23. A24 is twice of 24, which is 48, and so on. Now, you can easily conclude that your nth term will be of what form? So, nth term is going to be an, representing your nth position term, is simply twice of n. So, this is a way to get the idea about nth term. In sequences, you must know about nth term, how your nth term looks like in this algebraic form. It is very, very crucial in sequences. Clear? Moving to next. Now some remarks. In the sequence of primes 2, 3, 5, 7, 11, and so on, we find that there is no formula for nth prime. We cannot guess, or we cannot, here we are not having any nth formula, any nth expression, as we saw in the previous one. So such sequence can only be described by verbal description. So in every sequence, we should not expect that its term will necessarily be given by a specific formula. Okay? However, we expect a theoretical scheme or a rule for generating the terms A1, A2, A3, An till infinity in succession. So very, very important remark. We are not going to expect that we are always end up with some nth formula. Clear? Moving to next. Now, sequence as a function. How we look sequence as a function? So, first of all, recall what is a function. Function is your relation first of all. Let me just count you some points of function. Function must be your relation first of all. If you are having a relation A to B, set A to B, set, non-empty sets, and that relation is a function, meaning first of all your domain must be the complete set A. And for every element of A, the domain set, from the domain set, we must have a unique image, one and only one image. So just think like function is your machine, which if you give input, you must have exactly one output. You are not going to have two different output for a single input. Yes? Now, the same will be applicable over here. So a sequence can be regarded as a function whose domain is the set of natural numbers. So in this case, sequences, the domain is going to be the set of all natural numbers. Or sometimes it totally depends how we are describing it, or sometimes, or some subset of it. Clear? Sometimes we use the functional notation, what? AN, for this. So F n to x set. So we define Fn, our sequence as Fn is equals to nth position term. So n represents your nth position. So for each position, you must have some member of your sequence, some term, which is represented by an. An is nth position term. Simple. So domain of F is a set of natural numbers or some subset of it denoting the position of term. Simple. Moving to next. Let A1, A2, A3 till AN, we are having these terms, and these terms are from a given sequence. Then the expression A1, A2, A3, AN. If you are having your infinite sequence, the sum, the addition will be till infinite. If you are having finite number of terms, you have to add finite number of terms of your sequence. So this expression is simply, we are calling it as series. So this is what we call series. And this is how we associate sequence to series. Clear? So series are often represented in compact form using sigma notation, a Greek letter, this sigma, as means of indicating the summation involved. So this represents nothing but the summation. Yes? So if you are having finite sequence, meaning finite terms, say n, you are having finite terms n in a given sequence. So the series associated to the sequence is simply A1 plus A2 plus A3 till AN. You are going to add all the terms provided to you in the given sequence. Now this is your expanded form. Now how you are going to write this in the compact form using this letter sigma? Very simple. So we are going to use first of all this sigma. Now we are going to write some term. So AK. AK represents your term, each term. Okay? A1, A2, A3. Now we are not going to write some number to the subscript. We are using AK, K in general position, K, kth position, any position, kth position. Now what we are going to do is simply run this K from where to where? 1 to n, as we are adding from A1, A2, A3 till AN. So now writing K1 here to the bottom side of this sigma and to the top side of this sigma, the last term, from where to where we are going to run our summation? 1 to n. So this is our compact form of your expanded form. So this is same as this representation. Both represent the same thing. This is in compact form. This is in expanded form. Clear? How we are going to write any given expanded series form into a compact form. Let's see some related examples. So write the first three terms in each of the following sequences defined by. So first, an, meaning nth position of your sequence, is simply given by 2n plus 5. Second, the nth position of your sequence is simply given by n minus 3 by 4. Now for first, as given, nth position is simply, nth term is 2n plus 5. What you have to do is just find three terms, first three terms of your sequences. So for first three terms, we are going to substitute n1, n2, n3 in order to get the first three terms. So just substitute 1, then 2, then 3, and then just solve to get your nth position. So for a1, the first term is simply twice of 1 plus 5, which is 7. So first position member is 7. a2, second position term, simply 2 times 2 plus 5, which is 4 plus 5, 9. So second term is 9. a3, 2 times 3 plus 5, meaning 6 plus 5, 11. So third term is going to be 11. Simple. Therefore, the required terms are 7, 9, 11. Now for second, an, the nth position term is simply n minus 3 by 4. Just plug your n, get your nth position term. So for first term, a1 is simply 1 minus 3 by 4, which is minus half. So first position or first term is minus half. For a2, plug 2. So 2 minus 3 by 4 is simply minus 1 by 4. So second term is going to be minus 1 by 4. Now for a3, third term, simply put 3 here. So 3 minus 3 by 4 is simply 0 because the numerator becomes 0. So we are getting third term as 0. Simple. Hence, the first three terms are minus half, minus 1 by 4 and 0. Clear? Moving to next. This question. What is the 20th term of the given sequence? So sequence, the nth term of your sequence is simply given by n minus 1 times 2 minus n times 3 plus n. In order to get nth term, you just have to plug n. Simple. So solution. Putting n20, we obtain the 20th term simply 20 minus 1, 2 minus 20, 3 plus 20. Now 20 minus 1 is 19. 2 minus 20 is minus 18 and 3 plus 20 is 23. Just solve it. You will get a negative integer, which is minus of 7,866. So A20 will be your minus 7,866. So this will be your 20th term. Simple. Now this example. Let the sequence an be defined as follows. So first term is simple 1. Now we describe recurrence relation here. So as you all see that the upcoming term is totally depends on the previous term. So recurrence relation is there. So nth position term is nothing but n minus 1th position plus 2. So just add 2 to the previous term in order to get the nth position term. Simple. As we are already given that first position term is 1, so A1 is 1. So we are using this relation for n greater than equals to 2. Yes, why? Because A1 is already here. Now, first 5 terms you have to find out. And then write the corresponding series. Simple. Solution. We have the first term as 1 already given to us. A2, the second term. How we are going to get our second term? By using this recurrence relation. So just plug 2 in place of n. So A2 is simply 2 minus 1, which is 1. So A1 plus 2. And we know about A1, which is 1. So 1 plus 2, which is 3. Now this gives me the second term as 3. So first term is 1. Second term of my sequence is 3. Now for 3, the third position term, the third term, simply plug 3 here. So A3 is simply A3 minus 1, which is 2. So A2 plus 2. You can easily observe from here what we are doing is, in order to find nth position term, we have to add 2 to the just previous term. So A2 plus 2. A2 is 3. Adding 2 to, we are getting 5. So third term of your sequence is going to be 5. Now A4, the fourth term, plug 4. So A4 is A4 minus 1, which is 3, 3 plus 2. A3 plus 2, A3 is 5, so 5 plus 2, meaning 7. So fourth term is going to be 7. A5, the fifth term, plug 5. So A5 is A5 minus 1, which is 4, A4 plus 2. A4 is 7, 7 plus 2, so 9. Fifth position, a fifth term is simply 9. So now you are having your first 5 terms, 1, 3, 5, 7, 9. Now it is very easy to find its corresponding series. So 1, 3, 5, 7 and 9 are the first 5 terms, and the corresponding series of this sequence is going to be add 1 plus 2 plus 3. Sorry, 1 plus 3 plus 5 plus 7 plus 9 and so on. Yes, as we are having our infinite sequence. This is your what? Infinite sequence. As you just n belongs to the greater than equals to 2. So you just plug n, you will get your successive terms. So this is your infinite sequence, and simple. I hope now you have idea about sequences and series, how we define what are recurrent sequences. Clear? So this is it from this session. Thank you.